The objective of particle physics is to understand the basic structure and laws in nature, all the way from the largest dimension in the universe, formation of galaxies and stars, all the way down to the smallest dimension in the microcosm.
So historically we knew about all of the different elements in nature. We knew about helium, hydrogen, oxygen, gold, lead and so on, which are all made of different atoms. But a great simplification was made when we realized that all the atoms are just made out of three particles, the protons, the neutrons and the electrons. And just by adding more protons, more electrons, we get a different element, a different type of atom.
In principle, you can build a very simple universe with just protons, neutrons and electrons.
But it became much more complicated in the beginning of the 20th century when we found many, many new particles from cosmic rays.
There wasn't really a system established to organize this zoo of particles.
So we were calling these new particles things like pi, sigma, delta and so on, and things got so bad we were running out of symbols to name these particles. So we started organizing these particles according to the properties they have. And the properties are things like spin, electrical charge, so if they're positively charged, negatively charged or neutral, mass of the particles, and the lifetime of the particles, which is how long it takes before they decay into lighter particles.
To simplify the picture, new fundamental particles called quarks were predicted. And the whole zoo of particles could be described by combinations of these quarks. And this was the birth of the Standard Model. At the beginning, there were only 3 quarks. Then a 4th, 5th and 6th quarks was predicted and then discovered, and this gave us great confidence in the model. In addition to these quarks, there's another set of fundamental building blocks of matter, the so-called leptons. They are composed of an electron, their heavier cousins, the muon and the tau, and their neutrino partners. In addition to the fundamental building blocks of matter, the Standard Model also incorporates the fundamental forces. The exchange particles of the weak force are the W and the Z boson. The weak force explains the energy production in the Sun and is responsible for the radioactive beta decay. The electromagnetic force acts on charged particles. The corresponding force carrier is the photon. The electromagnetic force is responsible for propagation of light or for the fact that a magnet can pick up a paperclip. The strong interaction acts on the quarks. The corresponding force carrier is the gluon. The gluon literally glues together the quarks in the neutrons and the protons, and it holds the nucleus together.
The Standard Model is extremely successful, and it has predicted all the phenomena we have seen so far at the microscopic level.
This is a beautiful theory. It is self-consistent, it's predictive, but it's incomplete. There's one last missing piece of this puzzle. That's the Higgs boson. It's the holy grail of particle physics.
We know exactly what it should look like, and we have predicted this particle since over 40 years, and we use it in all our calculations and so on. We're pretty sure it's there, but we haven't found it so far. And now the LHC, which is already running, taking data, will find this particle if it exists. So this is the final piece of the Standard Model that we're looking for right now.
But there are still many unanswered questions beyond the Standard Model.
Some of the things that Atlas could discover that are beyond the Standard Model are things like dark matter, supersymmetry, or even extra dimensions.
All these open questions point to the existence of new particles which could be discovered and studied here at the Large Hadron Collider.